Hi, I'm Bill, and I'm here with my friend Lynn, and we're going to create an electronic circuit on this breadboard that will provide power to this pump so that your plant can be watered at just the right time. The power will go through this switch, which is just a transistor that can be turned on and off by this microcontroller, whose job is to count time so that every 24 hours your plant gets watered. Okay? Breadboard has two purposes. First purpose is to hold the parts in place so they don't fall out.
Okay.
And the second purpose is to make electrical connections. And the way the electrical connections work is that columns are connected. So these 5 squares are connected, these 5 squares are connected to each other.
So inside this breadboard, there are conductors and insulators because
Yes.
Some of it's live or some of it makes the is allowed to conduct electricity and some pieces are not. So
Correct.
It's like a wire that's taking the shape of a board or a box.
That's correct.
Okay.
I think you'll understand better how the electrical connections work if I show you what's inside this green breadboard. This is a conductor that runs the entire length of the column, so that all of those holes along one of those columns are connected. So when you push the lead through one of those holes,
And actually you
this
can
thing
see
grabs it, and in fact we might even be able to take one of these
When you're
out.
holding it up to the light, you can see now those metal bars in the holes.
So different than I thought.
You can see the 5 little things that grab the wires.
Yeah.
You're going to poke through those holes, and then it just makes the connection that way. That's all there is to it. Okay, so that's the basic idea of the breadboard. And we're going to be putting some wires and some parts in the breadboard. There are 7 wires. That's it. And you can see them on this picture here, how they connect.
So it's
So you
gonna,
follow the diagram, and if the diagram has an orange wire, you pick an orange wire, and it'll be just the right length.
and I can already tell it's not going to go in there very easily.
Yeah, you wiggle it a little bit, and you'll get the hang of it. Yeah, there you go.
Okay.
Perfect. That's exactly right.
And then-
A tip
Yeah.
is that if you accidentally bend one of these wires and it's no longer nice and straight, you can always fix it by squeezing it with the pliers. It's perfect.
Okay,
There
great.
you go. You're
So far,
on
so
a
good.
roll. One thing that's a good idea is that when you've got a classroom of kids doing this, when each kid finishes, have them exchange the boards and inspect each other's work.
That's a good tip.
Is something that we do.
Yeah. Okay. And then gray, which is 1 over.
There you go. So we're going to put in a resistor, and its purpose is just to control the amount of current that flows, because we need very little amount of current actually to turn this switch on and off. You can think of a resistor as like a water faucet,
Okay.
where there's a certain amount of pressure that comes from your water system. Maybe you've got a pump or municipal water, and there's a certain amount of pressure, whatever it is. But you want a variable amount of water pressure to come out of your sink, depending on what you're doing. And so you have a faucet that controls how much pressure comes out. That's really all a resistor is doing. Voltage is like pressure,
Right.
and current is like how much water is flowing, and the resistor lets you choose how much water, if you will, in our metaphor, we want to come out given how much pressure you're pushing.
Okay.
Now, it sort of comes like this. We have pre-cut the leads so that you don't need wire cutters.
Okay.
And the center part of the resistor is called the barrel.
This part.
All right, and what I'm going to do is I'm going to hold the resistor by the barrel like this and take my fingers and just go like this. All right, to make a little U-shaped.
So hold the barrel.
Yeah, hold the barrel and take your fingers and just make a little U-shape. All right, and then you might have to adjust the lead spacing a little bit with your fingers, but it's going to go in. And again, you'll need to wiggle some. And sometimes I have found that when I try to push it in, one of the leads, and by the way, the wires sticking out are called leads. And sometimes one of them bends a little bit. Looks like you got that in just fine. Perfect. All right, and then what I would do, I would check. Yeah, that looks perfect.
And what are you looking for when you change?
What I'm looking for is to make sure that that one of the leads didn't get bent, didn't actually go in the hole, but rather just got bent. And you can fix that with the pliers. You can take the pliers, all right, and you can give it a squeeze and straighten it out.
Okay.
So the next step is to put in the transistor. The transistor acts as a switch, allowing the computer to switch current on and off, which will turn our pump on and off. Well, you'll notice the transistor's got 3 leads. 2 are for current coming in and going out. The third is to receive a control signal from our computer saying whether our switch should be on or off.
Okay.
Okay? And the transistor now, this is the first device that has to go in a certain way. And if you notice, it's got essentially, you could hold it with this metal tab in the back or in the front. And if you look at the picture here, it's kind of the idea of this picture is that kind of salmon colored thing represents this metal tab. That tells you which way to hold it when you stick it in.
All right.
So give that a try. So you hold that as shown in the diagram, there you go. And you can see which wires, yeah, exactly. So I kind of wiggle it back and forth a little bit and, you know, give it a little bit of push, and if one of the leads accidentally bends, you'll see it, and we can go fix it. How'd that go?
Now, does it sit flush, or does
Just
it
like
stay
that
up
is fine.
this? Okay.
And the purpose of this metal tab is to dissipate heat.
Okay.
At this point, we've completed our basic RoboPots circuit. When it is turned on, current will flow from here, where we'll plug in our battery, through the breadboard to the gray wire, which will carry it down here, and through the breadboard to here, where we'll plug in our pump. The current will flow through the pump and then back out of it here, where it will travel down the breadboard to the yellow wire, which will channel it back to a spot where it will connect through the breadboard with the transistor switch. Current will flow through the transistor and then via the breadboard to the brown wire, which will carry it to a point where it can connect through the breadboard back to the power source. This completes the circuit. Now, I've said that the transistor acts as a switch. When the transistor is on, the circuit is complete and current will flow around the circuit. The pump will turn on, watering the plant. When the transistor is off, the circuit is broken, current will stop flowing, and the pump will shut off. But how does the transistor know to switch on for a few seconds every day? It's told to by a voltage signal sent to its third lead. When that voltage signal is sent, the transistor turns on, and so does the pump. That leads to another question. What sends the signal to the third lead? That's where our computer comes in. Let's look at this broader view of the breadboard we've been assembling. Here's our transistor. Its third lead connects through the breadboard to the resistor that we installed. The resistor then connects through the breadboard to the brown wire, which leads through the breadboard to this big blue thing, which is our microcontroller, or computer. Okay, the only thing left to do is to plug in the computer.
Okay.
So that is in this little pink static protecting bag, so if you pull that out, and once again, this is the kind of thing that where it does matter which way it goes in, but that should be pretty easy to see. This metal connector that's on one side corresponds to that thing here, this little square here. And this metal connector allows you to hook this computer up to your laptop, all right, a Macintosh or a PC, if you want to change the software. That's what this connection is for.
Okay.
Okay, but that's a little bit of an extra. So you're going to drop that in, you're going to push that into the holes.
So this has to line up according to our diagram.
Yeah.
So
now you see these?
Oh, I'm
see these
here.
things
I'm
here?
one
That's,
over.
Exactly.
Okay,
That's
why.
those little orange circles tell you where the pins are.
And I'm one behind the green, so I'm okay. And two here. Same kind of feel as the other.
Yeah, that'll just drop right in, and those pins are pretty sturdy. They're not going to bend.
There it goes.
There you go. That's it. You got it.
Got it.
Okay. The computer itself is this little microchip right there. that little square microchip. And inside that little microchip, I don't know what the exact count is, but there are probably a few 100,000 transistors in there.
Wow.
Okay? This computer is about half as powerful as the computer that was in the Apollo command module landing on the moon.
Wow.
Okay? However, this computer is obviously much smaller and consumes much less power.
Is the computer that's in this similar to what would be in a cell phone?
Great question. It is not all that similar because the computer in a cell phone is much more powerful.
Okay.
To do the graphics, the computer in your cell phone is probably 10,000 times more powerful than this.
Okay.
And by that I mean speed and memory.
Speed and memory, okay.
It's probably got 10, maybe even 100,000 times as much memory,
Wow.
and maybe 10,000 times faster.
Wow.
We are now finished assembling the electronic parts, and we will be switching to the mechanical assembly.